Right now, beneath the Pacific Ocean off Oregon's coast, the seafloor is rising. Sensors buried in total darkness at 1,500 meters depth are recording something that has not stopped for a decade. A volcano is inflating. It is swelling upwards centimeter by centimeter, pushing the ocean floor toward a threshold that scientists believe will end in eruption. And deep in the Oregon interior, a lake of impossible blue fills the wound left by the last time this region's geology lost control. That lake is 592 meters deep. It exists because a mountain once stood here and then, in a matter of days, ceased to exist. What destroyed Mount Mazama 7,700 years ago? Could the volcano rising beneath the ocean repeat that catastrophe? And if the sensors go silent before the answer arrives, who will be watching when the seafloor finally breaks? The Klamath people called it Giwas. They considered the lake a sacred place, a portal between the human world and the spirit world. Their oral traditions describe red-hot rocks the size of hills arcing through the sky, forests consumed by rivers of flame, a mountain collapsing into itself until only a vast emptiness remained. For generations, many Klamath would not approach the caldera rim. The place was regarded with both reverence and dread, because powerful and dangerous beings were believed to inhabit the water below. Only those who were physically, mentally, and spiritually prepared dared to venture near the water. One Klamath elder described the place simply: it was powerful. Too powerful for ordinary people. But this was not myth alone. Archaeologists have found sagebrush sandals buried beneath layers of Mazama ash at sites across the region, including Fort Rock, roughly 100 kilometers to the east. People were living in the shadow of this mountain when it fell. The stories passed down for 7,000 years are not legend, they are testimony. What tourists see today is a postcard. Water so clear it once held the world record for clarity, cradled in a ring of forested cliffs. What geologists see is a scar. The caldera stretches 8 to 10 kilometers across and plunges more than a kilometer deep. Something colossal was removed from this landscape. Before the collapse, Mount Mazama stood roughly 3,700 meters tall. That would have made it Oregon's highest peak, rivaling Mount Fuji in stature. It dominated the southern Cascade Range, a chain of volatile peaks that includes Mount Rainier and Mount St. Helens. But Mazama was not a single cone. It was a complex system of overlapping shields and stratovolcanoes, each built atop the bones of its predecessor. According to the United States Geological Survey, this volcanic construction began approximately 420,000 years ago. The first eruptions formed Mount Scott, now a modest summit east of the caldera rim. Over hundreds of thousands of years, older volcanoes went extinct and new ones grew to the west. Layer upon layer of lava and pyroclastic debris accumulated, visible today in the caldera walls like the pages of a stone book. And the system never stopped evolving. Each new eruption shifted the architecture. Glaciers carved U-shaped valleys into the flanks, and lava filled some of those valleys while leaving others untouched. Mazama was not a sudden anomaly. It was a patient, relentless engine of construction, building itself toward what we can now recognize, in hindsight, as a system that could not sustain its own growth. But something changed. Around 30,000 years before the final collapse, Mazama's behavior shifted. The eruptions grew more explosive, and thick flows of silica-rich rhyodicite lava began oozing from vents high on the mountain. The USGS identifies the Grouse Hill and Red Cloud Cliff flows, erupted between roughly 30,000 and 25,000 years ago, as early evidence of this dangerous transition. Silica content determines a magma's personality. Low silica basalt flows like warm water, spreading easily and releasing gas with little violence. High silica rhyolite behaves like hot honey. It traps gas inside, building pressure with no escape. Imagine shaking a bottle of water and opening the cap. The water splashes. Now imagine doing the same with a bottle of thick syrup that has been superheated.
The cap does not pop, it explodes. That was the new Mazama. Deep beneath the mountain, a reservoir of this volatile magma was growing. When it finally erupted, the USGS estimates it expelled approximately 50 cubic kilometers of magma in dense rock equivalent. For scale, the 1980 eruption of Mount St. Helens expelled about 1 cubic kilometer. Mazama released roughly 50 times that amount. The pressure was building toward a threshold the mountain could not contain. The evidence that the system was nearing failure arrived in a final, ominous signal. Shortly before the climactic eruption, a vent on Mazama's north flank produced the Cleetwood lava flow. When the caldera later collapsed, the geological evidence suggests that flow was still hot enough to pour back over the new rim and down into the depression. Based on what we know, this implies the lava had not even cooled before the mountain beneath it vanished. The interval between the last warning and total destruction appears to have been extraordinarily short. There may have been days, there may have been hours, and then the mountain tore itself apart. The eruption began from a single vent on the northeast flank. A towering column of pumice and ash punched upward to approximately 50 kilometers altitude, the boundary of the stratosphere. At that height, the column would have been visible for hundreds of kilometers. Winds caught the ash and carried it northeast across the continent. Within days, the pale blanket reached central Canada. Fragments of Mazama's destruction have been identified in 8 American states, 3 Canadian provinces, and in ice cores from the Greenland ice sheet. The total area blanketed by ash covered at least 900,000 square kilometers across the northern Great Plains alone. The National Park Service estimates the total ashfall zone extended across more than 1.7 million square kilometers, an area roughly the size of Alaska. But the column was only the beginning. As the magma chamber emptied, the summit lost its structural support. Circular fractures opened around the peak like cracks spreading across a windshield. Magma surged through these ring vents, feeding pyroclastic flows that raced down every valley. Superheated avalanches of gas, rock, and ash traveled as far as 70 kilometers from the summit. Valleys were buried under up to 100 meters of debris. The total volume of erupted material reached approximately 176 cubic kilometers. The mountain's height dropped by more than 1,600 meters. Where a peak rivaling Fuji once stood, there was now a hollow depression 8 kilometers wide and more than a kilometer deep. The National Park Service classifies the event as VEI 7, one of the most powerful eruption categories ever recorded, though some databases place it at VEI 6. By either measure, it ranks among the largest eruptions of the past 10,000 years and was roughly 40 times more powerful than the 1980 eruption of Mount St. Helens. What had taken 420,000 years to build was unmade in days. The destruction did not end at the caldera rim. Aerosols injected into the stratosphere spread across the northern hemisphere, blocking sunlight. Analysis of Greenland ice cores indicates the eruption produced atmospheric loading over roughly 6 years. Researchers estimate a temperature drop of 0.6 to 0.7 degrees Celsius at northern latitudes, persisting for 1 to 3 years. The cooling echoes a more recent catastrophe. In 1815, Tambora's eruption produced the infamous Year Without a Summer. Archaeological evidence from southern Alberta suggests that humans may have abandoned some Mazama ashfall zones for as long as 200 years. Based on what researchers can infer from the sediment record, the disruption to food sources and water systems could have made the region uninhabitable for generations. Rain and snowmelt began filling the caldera almost immediately. Over centuries, the depression became a lake 592 meters deep, the deepest freshwater body in the United States. Its extraordinary clarity is a product of isolation. No rivers flow in or out, and the water is filtered through volcanic rocks so thoroughly that organic nutrients are almost non-existent. But beneath the surface, the volcano is not finished. The USGS classifies Mount Mazama as dormant, not extinct. Wizard Island, the small cone rising from the lake's western shore, proves the system remained active as recently as 4,800 years ago. Smaller eruptions are considered likely in the future. The scar is healing, but the engine beneath it is not dead.
Now shift your gaze westward. Leave the forests of southern Oregon behind and cross 480 kilometers of open Pacific Ocean. Past the continental shelf, past the abyssal plains, you reach a ridge where two tectonic plates are pulling apart. Here, rising from the Juan de Fuca Ridge, sits Axial Seamount. It is the most active submarine volcano in the Northeast Pacific, and based on a decade of steady inflation, scientists believe it is building toward its next eruption. The question that follows is inevitable. Could Axial repeat what Mazama did? Scientists say no, and the distinction is fundamental. Mazama was born above a subduction zone, where oceanic crust dives beneath the continental plate. That process generates the silica-rich, gas-trapping magma that fuels catastrophic explosions. Axial sits on a mid-ocean ridge, where plates spread apart rather than collide. Its magma is basaltic, low in silica, fluid and hot. Think of the difference between thick caramel and warm tomato juice. One clogs, traps, and detonates. The other flows freely. This is why Axial's eruptions reshape the seafloor, rather than obliterating it. But the two volcanoes share one haunting feature. Both possess calderas born from collapse. Axial's rectangular summit depression measures roughly 3 by 8 kilometers, bounded on 3 sides by faults up to 150 meters deep. Beneath the caldera floor lies a magma body approximately 1 kilometer thick and 14 kilometers long. When Axial erupts, magma drains from this reservoir and the caldera floor drops. After the 2015 eruption, seafloor instruments recorded a deflation of 2.4 meters over a matter of days as magma drained from the reservoir. Then the cycle began again. Magma refilled the chamber, the floor rose. That rising has not stopped since 2015.
Axial Seamount is the most monitored submarine volcano on Earth. The National Science Foundation's Ocean Observatories Initiative has wired more than 140 instruments across 900 kilometers of seafloor cable. Seismometers track every tremor, pressure sensors measure every centimeter of inflation. Hydrophones listen for the deep rumble of magma shifting through fractured rock. Researchers at Oregon State University, the University of Washington, and NOAA receive this data in real time. The seafloor streams its vital signs directly to shore through fiber optic cables running back to Pacific City, Oregon. This network captured the 2015 eruption in unprecedented detail. It also recorded the eruptions of 2011 and 1998, building a pattern that scientists hoped would predict the next event. What happened next surprised even the researchers. By late 2024, inflation had reached 95% of the pre-2015 threshold. Volcanologist Bill Chadwick of Oregon State University forecast that Axial would erupt by the end of 2025. But the rate slowed. Seismicity remained lower than expected, hovering around 100 to 200 earthquakes per day. The forecast shifted to mid to late 2026. Based on current data, a new hypothesis suggests that roughly 500 earthquakes per day may be needed to trigger failure, though this threshold has not yet been tested by an actual eruption. A parallel effort launched in November 2025 pushed the science further. Researchers from Uppsala University and ETH Zurich began feeding Axial's real-time data into a physics-based failure model, the first of its kind applied to an active volcano. Each monthly forecast is cryptographically sealed before release, preventing hindsight bias. It is the most transparent eruption prediction experiment ever attempted. But the experiment faces a threat that has nothing to do with magma. Proposed federal budget cuts could slash funding for the observatory by 80%. If the cables go dark, the instruments fall silent.
the most watched volcano in the ocean would go blind just as it approaches its moment of truth. Emergency funding has secured operations through summer 2026, but the long-term future remains uncertain. Mazama erupted without instruments. Axial may erupt without funding. There is a deep irony in Oregon's geological story. Inland, Crater Lake exists because no one could monitor or predict what Mazama did 7,700 years ago. Offshore, Axial represents the opposite, a volcano made safe not by its nature but by observation. Its eruptions pose no threat to people. The seamount sits too deep and too far from shore to generate tsunamis. Lava will flow across the seafloor, reshaping terrain and feeding hydrothermal ecosystems. If the instruments survive, scientists may be able to live stream the eruption as it happens. This could mark the first submarine eruption ever observed in real time from start to finish. One Oregon volcano left a lake so deep it swallowed a mountain's memory. The other is writing its story 1 centimeter of inflation at a time. But the Earth does not operate on human schedules. The sensors measure what has happened, not what comes next. Somewhere between a sacred lake and a wired seafloor, the same restless forces that built and destroyed Mount Mazama are still at work. The deepest lake in America was once the tallest mountain in Oregon. The most monitored volcano in the ocean has not yet revealed its next move. When the ground decides to break, will anyone be listening?